We want to talk about homotopy lifting property. So you have a projection map from space y to space x, and you have this homotopy h, say between two continuous maps f and g, and you want to be able to lift this homotopy to h tilde such that this map f gets lifted to something like f tilde. So let us make this more precise. So first of all, you are given a projection map and you are given K, which is a compact space. And you are given that this diagram will commute. So you have a map F, which is a continuous map from K to X. You are given the projection map, and corresponding to F, there is another map F tilde, which goes from K to Y. Now we have to prove, suppose we have a homotopy. Now before we define a homotopy H here, we have to give another map. So you have another map from K to XG, and you have a homotopy H between F and G. So this H is homotopy between F and G, and we want to lift this homotopy to H tilde. So we have to show that there exists this homotopy H tilde if these conditions are satisfied such that this diagram will commute, and this H tilde will be equal to F tilde of K for all K in K. So let us go through it again, what I've just said. So you have a projection map, you have K, which is a compact space. You are given this commutative triangle that K to X gets lifted automatically to F tilde, and you have a projection map. And then you are given another continuous map G from K to X. This H defines a homotopy from F to G. So this is a homotopy from F to G. So homotopy from F to G. And the theorem says we are able to lift this H to H tilde here so that this diagram is commutative. So let us see this. So just like in previous case, you have a open cover of space X, and all these sets are evenly covered by P. So these are evenly covered. So as before, you split I into small intervals of length 1 by n. So this 1 by n is a big number. You could choose n something is very large, so 1 by n would be very small. And then correspondingly, since K is compact, it's a compact space, you pick up a finite cover of K by open balls, and each of these balls has radius 1 by 2n. So we are deliberately choosing this cover of 1 by 2n. And then, these balls, name them as K1, K2, K3, K4 all the way to Km. So these are the corresponding closed balls, and each of these balls have radius 1 by 2n. So each of this, for each ij, this kj, you pick one of these closed sets kj times this small part of the interval I. So this is small part of the interval I. This lies in the ball centered at kj comma this. So let us try to understand this statement here. So we are going to talk about this now. So say you have this interval I here. So these small squares represent breaking up of the interval. So this small part is going from, say, 0 to 1 by n. Then this part is going from 1 by n to 2 by n. And say we have the ith part right here. So this small split is from, say, I minus 1 by n to I by n. So this was the interval I. This side is the compact set K, and we have the corresponding balls. So you have K1 here, K2 here, and say Kj is lying somewhere here. So Kj times I minus 1 by n comma I by n, we are talking something about this square. So this is exactly the square we are talking about. So this is nothing but this square. Now kj itself is contained in a ball of radius 1 by 2n. So if I choose the midpoint of this square, then this entire square will lie in a ball of, say, radius 1 by n. And now we need to choose the center of this square. So say kj here, this big kj, say is in a ball with center small kj and then radius 1 by 2n. So we have a point here. This point has coordinate corresponding to this capital kj, which is small kj, and then midpoint of this interval. So midpoint of the interval, so this is nothing but I by n minus, so midpoint of the interval would be 1/2 of the length of the interval, which is I by n minus I minus 1 by n. This thing plus I minus 1 by n. So we are taking midpoint of this distance and then adding it to I minus 1 by n, and you can just see this will just come out to be 2i minus 1 divided by 2n. So the midpoint here, this kj corresponds to, small kj corresponds to this kj, and then midpoint of this interval is 2i minus 1 by n. So these are the coordinates of this red point. So ball around this red point, comma 1 by n. So this is contained within this ball. So you have obviously two indices here. You have j and you have I. So you have hij. Obviously n you have already chosen, so you don't have to worry about it. So hij is this homotopy h, which is given to us, restricted to kj times this interval. So now we want evenly covered sets of x. So xij will be hij kt times this thing. So that is part of the homotopy corresponding to this interval. So corresponding to this interval, we have the corresponding homotopy. So now since we had evenly covered here, x was evenly covered, so this is evenly covered by p. So this xij is also evenly covered by p. Therefore you can form such a map. You choose a map phi here, which is a homeomorphism, and this phi acts in such a way that this takes f tilde of k to fk comma dk. So dk is some discrete number, so just a number. Then it projects back onto dk. So notice that we are taking here I as 1. So this is just the standard projection map. This phi comes from evenly covered, and we have deliberately chosen phi so that p inverse of that particular xij, so I we are taking as 1. So for the first part, so first part of the homotopy, we are lifting to f tilde. So we are deliberately assigning f tilde of k, which is given to us, which will get mapped via projection. So this we are mapping to fk comma d of k. So how do you now define h tilde? So h tilde, you just define phi inverse of this h1j kt comma dk. So why did we make this construction? Obviously because this will give us a unique continuous lifting, since phi is a homeomorphism. So this will give us a unique continuous lifting of this h1j to this kj times 0 comma 1 by n to y, and this is precisely what we wanted. So we have gotten lifting from here, first part kj times 0 comma 1 by n, this part has been lifted to y. So we have gotten a small portion of h tilde, and it is such that h1 for I equals to 1, here if you just put 0, it will be f tilde of k, because f tilde of k via phi will go to fk comma dk. So this f just lifts to f tilde. Now you have to patch up all these h tilde ij to get h1 tilde. So h1 tilde is defined from 0 to 1 by n, but we need to patch up all of these hi tilde to get, like, from kj 0 1 by n we have to go to k times 0 1 by n to y. So how do we patch it up? So you can patch it up by the uniqueness of lifting. So if, say, you have I1 and I2, so ki1 intersection ki2, this is not empty. So in that case, the homotopy on the intersection would match. So there's going to be a uniqueness. This homotopy, this is this homotopy which is on this ki1 intersection ki2, this will get uniquely lifted to h tilde restricted to ki1 intersection ki2. So therefore, using these intersections, you patch up all these kj's to get k times 0 1 by n to y, and then again you have h1 tilde k of 0 as f tilde of k for all k. So now you can see that p times tilde here, h1 tilde is equal to h for all k. So if you just have k times 0 1 by n, then you can for the first part of the interval I, for 0 1 by n, we have been able to construct h1 tilde. Now similarly you can construct h2 tilde, h3 tilde and so on, and then you glue it together to get h tilde. So a quick overview. So you are given this diagram here, you're given a map G, you're given H. The idea is to construct this H tilde so that this diagram commutes. Now what we want to do is we want to construct H1 tilde, glue it with H2 tilde, H3 tilde and so on, and that will give us H tilde. And each of these H1, so H1 tilde corresponds to the interval 0 to 1 by n. So and H2 tilde goes from 1 by n to 2 by n. H3 tilde goes from 2 by n to 3 by n and so on. So how do we achieve it? So we just focus on H1 tilde first, and then you can say you can glue the end points. So for that, again you start by splitting I into small intervals, but you also have this compact set k to take care of. So you basically form a square like this. You take a general part of it, kj times this, take its midpoint, and this will be contained in a ball. Once it is contained in a ball, corresponding to that ball you can set up a homotopy hij. This will give you a evenly covered set xi comma j. That is it. Once you get this evenly covered set, then you know there is a homeomorphism phi like this. So once you have a homeomorphism phi like this, then you can just define phi so that this f tilde of k, because you are lifting some part here, f tilde, this f tilde gets mapped to f of k comma some discrete number d, and then you have d right here. And then you forget about this discrete number d, because this is just be a constant. This will just be some constant which you can just adjoin the way you feel like, because we have all these series of continuous maps. 0 1 by n is a connected interval all the way we go up to right here. So then you get h tilde of 1 comma j, which will give you phi inverse. So you set it up like this. And then you have the unique continuous lifting. You get different cages. You glue all these cages together because the lifting is unique, and that is what will give you the h1 tilde. Then you similarly construct h2 tilde and so on, and you paste them together because they are agreeing on the endpoints or the end intervals.